Chapter, who's going to tell us about solar microflares.
So good afternoon to all of you. So I will be talking about these observations and modeling of chromospheric evaporation during the solar microflares. So this work has been carried out in collaboration with Avik and Durgesh. So this is the brief outline of my presentation. So as from the title, you can make out that I will be going to talk about the solar microflares and the chromospheric evaporation. So I will talk about further about our observations which has been taken with the IRIS, Hinode and the SDO. And then I will present what are the parameters we have obtained as a results like intensity, velocity, density, temperature and the energetics involved in these events. And then using all these parameters, we will compare our results with this 1D hydrodynamic simulations, and finally I will summarize. So what are the solar microflares? So these are the small scale events, like they have an extent about 2 to 5 arc seconds, and they are very transient. They come of the lifetime of around 1 to 5 minutes or few minutes, and then they will observed first with this SXT, means solar soft X-ray telescope on Yokowo. So they are like very intense brightenings, which you can see, which have a very different distribution. So like they can be like a point like source or single loop like events or the multiple loop like events. So they are very transient and they come for a lifetime of just few minutes. So recently means like IRIS, which has a very high spatial resolution. So this has observed lot of transient phenomena. Some of them are classified with the different nomenclatures, and some of this can be classified as microflares. So next is the chromospheric evaporation. So exactly what happens? So if we release this impulsive energy is released into the chromosphere. So this leads to the heating of this chromospheric material. So this leads to the very high rise in the temperature, maybe let's say around 10 million Kelvin. So this high temperature released to this enhancement in the pressure, very high pressure. So this, because of that, the chromospheric hot material which starts moving up into the corona along the flare loops. So these are phenomena is called the chromospheric evaporation. Also this high pressure, because of this, the lower atmosphere has been pushed downwards. So the cool material which goes in the lower side of the atmosphere. So but as we know that the corona is lighter, so the hot material moves with the very high speed. So we get the very large blue shifts, whereas the cool lower atmosphere is denser, so the motion is very small. So we get the very small red shift. So if we can see this phenomena, basically that the high blue shift of the material moving into the corona and very small red shift of the material moving into the chromosphere. So we see that it leads to the chromospheric evaporation, basically the phenomena. So before I go into this our observation, so I just wanted to highlight, means with the IRIS line profiles, we see that different type of transients. So some of them are classified as a UV burst and some of them are the microflares. So if you see this movie, so they are like very small scale. So these, and this is also very small scale. So this is our spectroscopic slit which is sitting exactly on the top of this event. So we can capture the IRIS line profile. So if you see just the movie and with the image, there is not much different in these events. But if we see the spectrum, then there is a huge difference between the two events. So this is the study one is just a background spectrum. So during the event, this is how the profile is changing with the time. So you see that this profile is like its intensity goes very high up, and then profile is highly non-Gaussian in nature. Whereas for this case, this is a microflare, so there is not much distortion in the profile, but it still maintains the narrow and the Gaussian shape. So these are called as the UV burst. So intensity will go like 10 to 100 times than the background, whereas there is not much change in the distortion of these loops. So I will be focusing mostly on this kind of events. So before that, I will just highlight means this UV burst observation. So UV burst, like their time scale is also like a few minutes, but they can be recurrent in time. So we have a chance that one of the burst is happening here beneath the iris slit, so we can capture this line profiles. So you can see the evolution of the line profile with the time. So there are multiple events are occurring, and then it leads to the very high broadening of the line profiles. And on the top of that, we can see some of this absorption line features also. So this is the light curve from this slit GI imager from the iris. So you can see that there are multiple events occurring, and at the end there is a large energetics involved. So whether we see such events in the high temperature or not, so like iris is basically sensitive to the cool temperatures, like it's like 10 to the power 5 Kelvin. But whether this leads to the very rise in the temperature up to million Kelvin or not, so we can see whether the signature is seen in the AI passbands or not. So most of the events people see that UV burst, they have not seen the signature in the AI channels, but in this case we found some small signatures coming into the AI 171 and 193 channel. So they are like temperature can reach up to the 1 or 2 million Kelvin. So based on these observational parameters, we obtained basically what is the energetics involved. So using this density and the temperature obtained for these events, so we obtained that the energy is of the order of 10 to the power 27. So that's basically the falls in the microflare energy, but we don't call these as the microflares because we don't see any signature in the X-ray. So I will come on to these observations of this our microflares. So again, you can see this is the event basically. So this is the from the iris images, we can see this is very highly localized and very intense brightening, you can see, and our iris slit is just crossing on to this event. So this is the event which has been seen from the XRT also. So from there we concluded, okay, we see the signature in the X-ray, so it's basically a microflares. It can be classified as a microflares. So and this is visible into the other AI passband channels. So one of the interesting part which we see that this event which is occurring, it occurs in this HMI magnetogram. We see that it occurs in a very, there is a high magnetic gradient. Basically, I don't see any change in polarity basically in this region, but there is high gradient, like field changes from minus 400 Gauss to minus 50 Gauss from the compared to the surrounding, whereas one half is basically at very intense like 650 Gauss to the other half is at 120 Gauss. So there is a high gradient in the magnetic field, but there is no opposite polarity is present. So I couldn't conclude much from this magnetogram. So I will not use further for this part, but I will use mostly this intensity and the spectral profiles to do my further work. So we see this movie of this event in the different AI passband filters. So we notice that this event is very intense and brightening. It appears simultaneously. 2 moments they appear simultaneously, and also in all the filters they appear at the same time. So there is no time lag or something. So that was like one of the very unique feature of this event. And after this brightening, interestingly we found that there is a loop which appears in the iron in AI 131 channel and the 94 channel, and very weakly in the 335 channel, and not in the other channels. So that was one of the interesting part to visualize basically what exactly is happening in this filter. So we will focus more on the channels basically, what the dynamics of this loop which is newly emerging out. So this is the loop part which you can see. So like AI 94 channel, it has a contamination, like we believe that it forms at around the 7 million Kelvin, but it has a contamination from the school emissions which is coming from the iron 10 and iron 14. So that can be removed from this 94 channel. So using the approach of Delzana, so we can subtract out this component from the iron 10 and iron 14. So we can get from the 94 channel the contribution mostly from the iron 18. So this indicates that iron 18 is formed is like around 7 million Kelvin. So this could be very high temperature. And then we see this loop in the 131, and XRT also shows this very clearly. This loop is formed. So this indicates that this loop is really very hot. So what exactly is the temperature, that we will see further. So that's the basically the light curve at obtained at the different foot points. So I say as A and this is the B. So if you see the light curve, the intense brightening is just for 1 minute. So this is very sharp peak is coming, which is coming at the same time. And interestingly, we see there are multiple peaks in the many of these filters. So this part also we couldn't manage to explain exactly what could be the source of this multiple peaks, but I can understand, I heard from the many people that in the flares also sometimes you see these multiple peaks in some channels. And then if we focus on this loop top part, so we see that okay, the loop top is not becoming brightening at the same time in different filters, but there is a time lag. So it first gets brightened up in the 131 channel, after that into the 94 channel, and then into the 335. So we need to do further analysis on this. Basically, we use this time distance analysis to obtain how fast the loop is getting brightened up. So we create this time distance plot along this hot loop. So we find that okay, loop is getting brightened up. There is a phase plot is showing, and then the speed comes around like from the 131 it comes around 200 kilometer per second. With the 94 channel, it's around 74, and with the 335 channel, it comes about the 50 kilometer per second. So there is a different speed at the different filters. So they are basically like a temperature dependent flow is moving. And also if we see that the loop is visible only for a few minutes, like one minute in the 131 channel, whereas it's visible for a long time, around 4 to 5 minutes in the 94 channel, and it waits very long time, about 20 minutes in the 335 channel. So the lifetime of this loop is also time dependent, temperature dependent. So this is like one of the characteristics of this loop. So we can find out whether about the lifetime of these loops. So we perform this DM analysis basically to find out what could be the temperature of these foot point and the loop. So we do this DM analysis using the code of HANA Encoder 2012. So this is the DM curve, which explains basically what are the different plasma components are present at different temperatures. So we fit this with the multiple Gaussians to isolate the hot component plasma. So there are many components which we fit, like a cool component, which is like a background corona is always present, so which we will see always there, and then the warm corona, and then the hot material. So hot material which is coming up basically during the transient events at the foot point as well as the loop top. So we see that the foot point, the temperature is like going more than a 10 million Kelvin. So that's around the log scale on 7, whereas at the loop top the temperature is like going up to the 8 million Kelvin. So indicates that these are the very hot events. So this is like upper part of the atmosphere. We see in the corona what exactly is happening. So we can come back into the lower atmosphere, means what exactly is happening into the lower atmosphere, into the chromosphere. So where we have this iris slit which is sitting on the one of the foot points. So we can measure this our spectral profiles. So these are the spectral profiles of carbon 2 and the silicon 4 lines. So this is the background line, means before the event. So after the event, how the profile has been changed. So you can see that this is basically redshift. So there is a small redshift. So means perihelion is been pushed down. So it's moving downward. So with the speed of about 20 kilometer per second. And also if we focus on the other parameters of the line profile, like intensity, velocity, and the width. So we see that there is a small changes in the velocity even before the transient has been occurred, and there is the width which shows even before there is a increase in the line width, which is happening even before the transient has been occurred, which has been seen. So indicates that even before the transient has been triggered, there is some signature which can find into the line width. So line width carries the information that something has turbulent energy has been increased, which even before the transient. So this can be like used as a precursor to understand basically how this type of transients are being triggered. So this part has achieved much of the focus from the people, means what could be the possible region for this enhancement in the line width. And further we obtain the density of this during the event, means what exactly is the density. So we use this density sensitive line pair of oxygen 4. These are two pairs which are the density sensitive. So we using this we can obtain the density at the foot point, which comes around 10 to the power 11.5. So this line profile was not present before the event and after the event. So this appears only during the event. So this line is been formed. So can be used for the density purpose. So using these parameters we can obtain, means what could be the possible energies involved in this event. So we can calculate the thermal and the kinetic energy of these events. So as we see that the event has been observed from the iris and the AI, so we divided into two parts. One is like a cool component of the transient, and other part is the hot component. So using the cool component, which what we obtained as a density, the temperature, and the velocity. Using this we calculated the energies involved is about of the order of 10 to the power 25. And we use this from the AI, we use this hot temperature component. So using the density, temperature, and the velocity, so we obtain the energy released to be of the order of 10 to the power 26. So this is like more of a microflare energy range. So using this, all these parameters means whether we can reproduce this kind of observation using this hydrodynamic simulation. So as we know that the corona is like has a high thermal conductivity and has a low plasma beta. So plasma is basically confined to move along the magnetic field lines. So we can study the evolution of plasma using only the hydrodynamic 1D hydrodynamic models. So we use these differential equations of this mass, momentum, energy conservation equation to study this evolution of this plasma along this loop. So we just choose the different parameters, like we use this coronal loop length about 20 megameters, which is based on our observations, the length of this loop, and we choose the radius of the loop to be 1 megameter. So in this case, we just choose a very simple model. We choose just the monolithic loop and put a microflares at both the foot points of the energy above 10 to the power 27. So this is how the temperature evolutions takes place. So we use just the background corona to be around 2 million Kelvin, and then we dump the energy at the 2 foot points, and then the temperature evolution takes place with the time. So we see that the time evolves. So loop temperature goes up to the 7 million Kelvin at around 200 seconds. So we can plot this similar to our time distance map. We can again plot the results from the simulation as a time distance plot. So this is a position along the loop, and this is the time how these things are evolving. So this is the basically temperature. So there is a rise in temperature along the loop, and the temperature can go up to the 8 million Kelvin. So this is very much sensitive to the amount of energy we dump. So we choose energy based on our calculation. So this is very much in the accordance of this. And then this is the velocity plot. So we see that there is a blue shift of the plasma is there. That means plasma is moving upward, and then it's like chromospheric evaporation which is taking place. So we convolve these results based on our AI channels. So we see that there is a plasma moving upward, the almost similar speed, but we see the presence of a loop top brightening in this our simulations. But as we see in the observations that there was no loop top brightening was present. So this is one of the unsolved problem we have, means why we don't see in the loop top brightening in our observations. So that's one of the questions which we have. So what exactly is the lifetime of this loop? So loop can be cooled down because of the several mechanisms like a conduction and the radiation. So radiative cooling time and the conduction cooling time is given by this equation. So conductive cooling time depends upon the density, temperature, and the length of the loop, whereas radiative cooling time will depend upon the density, temperature, and the radiative loss function. So we obtain, based on our obtained parameters, we obtain that the conductive cooling time is about 42 seconds. So as we see that the loop was visible only for a short duration in the AI 131 channel, so that matches well with this lifetime. So initially the loop is getting cooled down by the thermal conduction, and then if we combine both the conduction cooling time and the radiative cooling time, so that will be given by this equation. So that comes observationally by about 20 minutes. So that matches very well with our loop observed in the 335 channel, which has a very broad temperature response. So these are the points which we can obtain from this analysis. So I will just briefly describe this one of the event which we see. Like we see that the iris observes lot of transient events, and it observes lot of formation of the new loops. So if you see that there are new loops are getting formed in the iris, so they are like basically the cool loops. But if we see AI images 94 channel, which is like a hot channel, so here we see that the loop is appearing only for the one of these loops, not the other part one. So it indicates that there is a formation of a hot and cool loop is taking place. So they have a different characteristics. So if we see in the more in the detail, so we find that I find that there is a flux emergence and cancellation is taking place at the foot point of this hot loop, whereas no such thing has been observed for this cool loop. So as you see that the iris slit is crossing through this loop, so it was good to find signature of this loop in the spectral diagnostics. So if you see, this is the imager, slit J images of the loop. So this is very clean loops are there, and with this spectrometer which was scanning the loop, so we found that the loop is visible into the spectral image also. But this is not the simultaneous image. But we are able to capture some of part of the loop. So we obtained this line width map. So if we see that, compare this line width. So this is the hot part of loop. So line width map is showing very small enhancement in the line width, whereas if we see this cool loop, so there is a huge enhancement in the line width. So that's like one of the new thing which we find, that even though the loop is getting hot, the energy released in the turbulence form is very less, but the cool loop shows a lot of turbulent energy release. So this could be one of the possibility that where the energy is going, basically whether the energy is going into as a thermal or it's going into the turbulent energy release. So possibility could be that where this type of events are occurring, at what height. So like they are occurring much lower in the atmosphere, so it might be possible that they are not able to reach, temperature is not rising very high up, but all the energy is released as a turbulent energy. Whereas if it's occurring very high in the atmosphere, so its possibility is that the temperature energy is released more into the thermal energy and as compared to the turbulent energy. So one of the deciding parameter could be the plasma beta, means at exactly what plasma beta such events are occurring. So which leads to the formation of either hot loop or the cool loop, or sometimes even not a loop, just one simple brightening like this case. So this is also one of the events which has a very huge broadening, you can see, but there is no loop is coming out at this point. So that's one of the thing which is still needs to be answered. So I will summarize myself here. So we see this UV burst, and these are very recurrent on the time scale of 3 to 5 minutes, and we see this simultaneous brightening of 2 foot points of the microflares and associated loop brightenings, and the density and the temperature can go up to 10 to the power 11.5 and 8 to 10 million Kelvin, and then this leads to the hot plasma moving upward, whereas the cool plasma moving downward. So that's the signature of the chromospheric evaporation, and the lifetime of this loop is temperature dependent. And we were able to reproduce some of the observations using this 1D hydrodynamic simulation, but some of these observations like loop top brightening is been not seen. And then we find that thermal conduction is the dominant cooling mechanism for this loop observed in the 131 channel. So
Okay, thank you very much. Very nice talk and good timing. So questions, please. Yes.
I was very curious to see that magnetic field change in one of your slides, sudden increase. So could it be because the line profile while taking the HMI magnetogram has changed, giving us artifact like a magnetic field change? And second part is, does it accompany all the time when these events happen? Does this magnetic field signature come all the time?
yes, actually, like in this event, yes, in this burst event, during, so when this burst occurred, there is a change in magnetic field which we see. It also fluctuates with this 10.
Yeah, so that could be spurious. That could be spurious due to the way they take the magnetograms in HMI, because the intensity changes sometimes, and that upsets the procedures.
Yes, but when I check this continuum images, there is not much signature of
not
this
in the continuum.
Changing.
You have to go to the HMI line profile, which is not available. I mean, they have their own process. So it will be interesting to track these kind of events.
Okay, thank you. More questions?
So what's your interpretation of what's going on? Are these events like regular flares where there's reconnection above and then that leads to what you observe at the foot points?
Yes, so basically we assume that the reconnection is happening within this region only. So in the lower in the atmosphere. Yes, yes, yes. No.
Okay, thank you. Another question?
Yeah, do you see any hard X-ray emission like RESI for these events?
I did not check with the RESI whether even the observation is taken during that time or not. So I have no idea about the RESI.
Okay. Thank you.
They're very small events, aren't they?
Yeah, they are very small events. So I don't think RESI is sensitive enough to detect small.
Probably not.
I don't know about that. Yeah.
Any other questions? Okay, well, we'll move to the next talk. Thank you very much again. Very nice. The next talk is by Yamini, and it's the study of plasma flows in various magnetic structures in the solar atmosphere. You got the microphone? It's not.
Okay. Good afternoon, everyone. So I am Yamini, a final year PhD student at IIT BHU RNSC. So I work for the I study the plasma flows in the solar atmosphere, basically multi-wavelength and multispectral study of plasma flows. So due to, I wanted to discuss plasma flows in various magnetic configurations, but due to time restrictions, I'll restrict myself just to the closed field lines. So the outline of my today's talk will be, I'll briefly introduce the cool loops, which Krichesh has introduced a bit, and then I'll discuss the multi-height variation of Doppler velocities, how Doppler velocities vary at, with different heights, and how the new results which we get from those multispectral results were good enough to model the cool loop systems which are initiated by explosive events. So just to briefly introduce, these are these active regions are all manifested by these kind of coronal loops. However, and they have these kind of photospheric signatures at the foot point. However, these cool loops which we are going to talk about, these are not as fascinating as they look for the coronal loops. They are low-lying connecting loops, and they generally have they look something like this. So, yeah. So these are the three different sets of three active regions which are dominated by bipolar magnetic field lines. So these are the cool loop systems. As we can see from the averaged emission of three different lines, and these are generally dominated by opposite magnetic polarities at the opposite ends. So magnesium 2K corresponds to the mid-chromosphere. We are focusing on the magnesium 2K3 line, which is the core of the magnesium 2 line, and it is an optically thick line, so it is a double Gaussian line, and carbon 2 corresponds to the upper chromosphere, and silicon 4 corresponds to the lower transition regions. And then these are different loop systems, and they also have the opposite magnetic polarities at the opposite foot points. So as we saw from the Doppler maps of these loop systems, so this is just the loop system, this is just the parametric maps for the first data set which I just showed, and at for different lines. So magnesium 2K, carbon 2, and silicon 4, all the three lines shows the similar behavior. That is, one of the foot point is blue shifted and one of the foot point is red shifted. So there is so it just gives an indication of how the plasma is flowing in these loop systems. So the plasma is flowing from blue shifted foot point to the red shifted foot point. And also we see that there is, as Krichesh also said, that there is an increase in the line width at the red shifted foot point. So there, wherever there are blobs of plasma flowing, it is causing an increase in the line shift. And also these, so we chose few locations at the blue shifted foot points and at the red shifted foot point. Generally, these kind of flows are caused by siphon flows, which is due to the difference in pressure at the 2 foot points, and there is also they are also caused by some kind of explosive events or some kind of impulsive energy transients. So what we found out, we chose few locations at the red shifted foot points and few locations at the blue shifted foot points, and we saw that nickel 1, which corresponds to the upper photosphere, doesn't have much of the outflows. So these are the blue shifted maps for 3 different sets, and these are the red shifted maps for the red shifted Doppler velocity trend for the 3 different sets. So this one is for the data set. As we see that the in all the 3 data sets, the significant blue shift starts to happen at the carbon 2, which is at the chromosphere. Generally, in these kind of loops, it is conventionally considered that these flows are driven by siphon flows, which is due to the convective motions and pressure differences, while we found out that there is some kind of localized mechanism is also taking place in addition to these siphon flows to derive these kind of plasma flows in this loop system. And it was also well correlated with the this redshift Doppler velocity trend at the opposite end of these loop systems. So this result is already published in APJ paper, but with this new results, we wanted to try to simulate these kind of loop systems and how this parameter can help us to model these kind of. So so this is the first data set which we used, and here we see that this kind of loop system has active foot point at both the foot points. So the plasma is flowing. If we take it as a whole loop system, the plasma is flowing from both the direction. However, we have chosen a single a bunch of strands where the plasma is flowing from FP1 to the FP2. So and as we see that these are the parametric maps, and so these brightened foot points, both the foot points were dominated by these kind of explosive profiles. So silicon 4 is generally has narrow profiles, which generally has a wing of plus minus 50 kilometers per second. But here we found out that there were so approximately 10% of the, if we take this box and if we go for different profiles, there were approximately 10% of the profiles which showed the explosive profiles, which are characterized by multiple peaks at silicon 4. So this has been just to show, this is just to show that how explosive events profiles show, and we have tried to fit it with the 3 Gaussians, one for the red wing, one for the blue wing, and one for the core. So as we see that both the profiles are showing excess width, these kind of explosive events might be driven by very small scale magnetic reconnection, which shows the bidirectional flows. So so we used gravitationally stratified and magnetized atmosphere. So these are the ideal MHD equations which we have used to simulate the Pluto core, and this is the kind of magnetic configuration which we have used to show that so this is one of the blue shifted foot points where the magnetic field is emanating, and this is the another foot point where the closed magnetic field is converging. And this is again the temperature profile of the solar atmosphere, which is generally we know. So carbon 2 forms at approximately 1.6 megameters, and so in order to simulate, we took this amplitude of 200 kilometers per second, and we gave the impulse at 1.6 and 1.6 megameter height, which is the formation height of carbon 2. So, and we were able to reproduce the cool magnetoplasma, which is emerging from one of the blue shifted foot points to the other. So these white lines are the magnetic field lines which we have used to simulate the realistic solar atmosphere. And this blue shows the loop systems, the whole loop system which we are taking. And here at 1.6 megameter, we give this impulsive pulse of 200 kilometers per second, and it derives the plasma and it flows to the other foot points. And it was able to exactly mimic the observations which we observed for these kind of cool loop plasma systems. And also, and this is how the density, so as we see from the density graph, the plasma is filling from one of the foot points to the other foot points of the loop system. And also the blue shift is changing to the red shift as we go. So this is along one of the strands along which we have taken the full this loop systems. So this is the concluding remarks of this work, that this simulation was able to mimic the observations which we observed, that is the plasma flows in the cool loop systems, which are driven by these kind of explosive events. Thank you.
Okay, very nice talk. Thank you. Questions? Comments?
So you drive this with this explosive event. So what are the different parameters of these explosive events, which is inputs for your model?
Yeah,
and
so
how do you, see the different behavior for different parameters?
So the different parameters were, one was this amplitude, which was 200 kilometers per second. Generally, silicon 4 has, even for this event, if we take an average profile from this box, we'll get a silicon profile of amplitude 50 kilometers per second.
Yeah, so that's, isn't it 200 is too high?
200 kilometers per second is high amplitude.
Yeah, so the question would be, have you tried with smaller velocities, which are more realistic, and see whether you can reproduce the results?
Yeah, we didn't try, but I haven't tried it yet. But
Yeah.
I think it won't give the plasma won't have enough energy to reach the other foot point if we give 50 kilometers per second. And also height was the next new factor which we implemented. Like generally, we give impulse at 0 megameters, which is the photosphere. But here we gave the velocity impulse at y is equals to 1.6 megameters, which corresponds to the function.
Yeah, so that is another thing which one can vary, that put this energy at different heights and see whether you see any difference.
Thank you. More comments, questions?
Did you look at the electron density from, for example, oxygen 4 ratios? I'm asking because if you find high densities, as you probably would, then if you remember, if you saw my plot yesterday, the carbon-2 could be formed at much lower temperatures than what normally people think if there is ionization equilibrium. So there might, be something useful anyway in general for your modeling to have an idea of the electron densities if you measure them.
So we took characteristic density at silicon 4 height. It is possible that some things might change if we change.
Yeah, if you've seen the oxygen 4 lines, it might be possible to, as
Oxygen 4 occurs at upper transition region, and generally oxygen 4 is very faint line. So
yeah, it is very faint. That's what Gurjesh was saying. You saw it occasionally. Yeah, you only see it when it's quite strong. But I think Julia's saying you could probably get a high density, and when you get a high density, that can change the ionization balance. So it means it shifts where different ions are formed. So has to be taken into account possibly. Any other questions or comments?
And I missed. What did the spectral line profile look like for magnesium-2 and carbon-2 at the 2 foot points? What this line is?
this is silicon
No, I'm talking about carbon 2 and magnesium 2 because you also measure shifts in those lines.
Yeah, so they, as I showed you, right, this trend doesn't show much of the high velocities at one magnesium.
No, that's okay. So I'm just asking how did the spectral line profile look? Because magnesium 2 is in these high density regions are usually doubly peaked, and so is carbon 2. So what reference wavelength did you take, and how did you measure the velocities? With which peak? For magnesium and carbon.
For magnesium and carbon. So for magnesium, that's why I said that I took the magnesium 2K3. So I calculated the Doppler velocity with respect to the core, and for carbon 2 I got the single profiles, the single peak profiles. There are regions when we get double peak profiles for carbon 2, but in our case we got single peak profiles for carbon 2.
Okay, thank you very much. Let's thank the speaker again. Jung-Chul Che, where is he? Is he here? Hey, okay, you're next. Yeah. Sorry. Yes, I've got the program right, haven't I? Sorry. Dynamically changing. Are you ready? Are you ready? Is that okay? Okay. Anybody else like to give a talk while we're waiting? Yeah. Already you're outdated. Sorry about that. Yeah, we had one speaker cancelled, so we shifted the talks up a little bit. So, Jung-Chul Che is going to talk about a comprehensive view of 3-minute umbral oscillations. Thank you.
Okay, I was waiting, so no problem. So I'll talk about, comprehensive view of 3-minute umbral oscillations. So my name is Jung-Chul Che from Oscillation University. Okay, so we all know there are two types of compressor wave, MHD waves. One is a fast wave, the other is slow wave. So in fast waves, magnetic pressure and plasma pressure work together in phase. So they move very fast. They usually propagate across the field line. The other waves are slow waves. So slow waves, magnetic pressure and plasma pressure compete each other. So they work against each other. So they have a very low speed, much lower than alpine speed and sound speed. They are mostly propagating along the field lines. The umbral oscillation I'll talk about correspond to slow waves. Okay, slow waves. So what are the umbral oscillations? Umbral oscillations are 3-minute period oscillation of intensity and velocity observed inside the sunspot umbrae, usually through the H alpha line or calcium to K line. So these movies demonstrate umbral oscillation. In continuum image, you do not see oscillation, but in H alpha intensity movie, you can see some, but they can best recognized in the H alpha Doppler movies. So why do we study umbral oscillation? We studied them because they are important. They represent the clearly detectable MHD waves in sunspot. They are actually correspond to slow MHD waves. There are no other MHD waves clearly detected in sunspot. These are the only kind. They may significantly contribute to heating and acceleration plasma in the upper atmosphere. And finally, they carry important physical information on the interior and atmosphere where they are generated and they propagate through. So it is very important to have a comprehensive understanding of these phenomena to make best use of them for this kind of stuff. So I'll briefly describe key observational findings which are already well established or which we recently found that have important observational constraint on the understanding of this phenomena. Firstly, umbral oscillations are not standing wave. They propagate upward. So multi-line observation clearly indicates there are phase difference among different lines formed in different layers of the atmosphere. They indicate these kind of oscillations propagate upward. So this is the phase difference map, which shows clearly about the propagation. Moreover, there are much observational piece of evidence that oscillation develop into shock waves. This is one example from iris observation of silicon 4 spectral line data. So this is time series of velocity determined from this line. Often we see sawtooth-like shape in this kind of stuff. So this is the evidence they are like shock waves. In this kind of wave analysis, shock wave signatures manifest this kind of second or third harmonic, high order harmonic. Then you can easily recognize they are corresponding to very steep change in velocity field. So this is the evidence of shock waves. The second important finding is that oscillation occur in packet. This is not well known. This is not well understood. But this is very important. Oscillation, 3-minute oscillation do not occur in a continuous way. They occur in packet like this. This is like some kind of wavy packet. So here we have one packet, which is clear in wavelength power spectrum. There's another strong wave packet, which is also clearly seen here. It may be 1 or 2 packets, I don't know. But anyway, the point is that they consist of a discrete packet. What is more important is that each oscillation packet is characterized by singly picked power spectrum. So there is one peak frequency, which is clearly is defined. So this wavelength power spectrum also says there is peak power spectrum. Of course, there is a finite thickness in the peak. That's also important. Also, it is well known that this kind of oscillation propagated not only in the vertical direction, but also they propagate horizontally, apparent transversely like this, as you see. In the penumbral area, they are known running penumbral waves. Even inside umbra, you see horizontal propagation. This is very interesting phenomenon because this has brought lots of confusion about the nature of physical identity of this kind of 3-minute oscillation. Because somebody says that this is evidence that they represent past waves. Actually, the propagation speed is very high. Typical speed is about 20 kilometers per second, which is higher than sound speed. But I said, this is not the real wave. This is apparent wave. They still should remain in the category of slow waves. We recently found a similar result even from the near the photosphere. We used the strong photosphere line, so we can determine velocity pattern near the photosphere. So we can find still very well-defined horizontally propagating pattern. They propagate out of some center, which we call oscillation center. So it looks like a ripple. So this is occurring even near the photosphere, which means that the source might be even below the surface. So this is a very important point. The final point is that the oscillation centers tend to locate it above umbral dot, inside umbral. Here is there are umbral dot, umbral dot, umbral dot, umbral dot. And these umbral dots undergo very rapid dynamical change, such as fast motion, splitting or merging, brightening, like this. So they represent very rapidly changing umbral dot, which we interpret is related to some kind of magnetic convection. So I'd like to present our compressive view of this kind of observation to understand the physics of the umbral oscillation. So this is the summary. Okay? So basically, we believe there should be impulsive energy, impulsive drive waves below the surface. So which we usually think due to impulsive magnetic convection, which suddenly release energy somewhere, they drive waves. So basically, the waves are fast waves. So they are propagate more or less like isotropically, but because of the refraction, they eventually come to the surface. But there is some time difference in arrival at the surface. Near the surface, there is a layer where plasma beta is close to 1. This is the point where mode conversion occurs. Then this kind of fast waves are partially converted into slow waves, which propagate along the field line, like this. And the first conversion occurs at this point, and the later conversion occurs this one. So we can see apparent propagation of the pattern from the center outward. This is what we observe. This is some simple, the result of a simple modeling. So we determined the distance from the oscillation center as a function of time from the data and presented the model. So we found that the propagation model with a source at the depth of about 2,000 kilometers below the surface can fairly well explain the pattern. So this is evidence that there should be some source. And we have some way of explaining the specific frequency. Why do umbral oscillation have a specific frequency, such as 3 minutes, or usually inside the umbral they are shorter than that, 2.7 or 2.4, 2.5 minutes, depending on the position. So we proposed a special way of explaining that. That's what we called photospheric resonator model. So the photospheric resonator is different from the previously known chromospheric resonator or subphotospheric resonator in that they are located in very shallow layer in the photosphere. So the bottom is characterized by the position near the low photosphere or slightly below the surface, which has the wave driving. And the top layer characterized by temperature minimum. So some waves near the cutoff acoustic cutoff frequency is partially reflected back. Then they interfere with the progressive waves and cause the resonance. So after resonance, this kind of wave is amplified, then they can escape out of the layer to observe as the propagating pattern, okay? Yeah. So this model can well reproduce the observed power spectrum, like this one. This is observation, and this is observation, and this model. So this is input power spectrum. So we can fairly well explain observed power spectrum, and we can also explain the observed velocity oscillation pattern like this. The dark curves, black curves are data, and blue one is a model, so they are fit very well. So our comprehensive view is like summarized like this. Impulsive events of magnetic convection occurred in the interior produce fast MHD waves propagating out of the region, and when these fast waves reach near the surface, they excite slow MHD waves by mode conversion. Because of the partial reflection at the temperature minimum region, the photospheric layer becomes a resonator for slow waves frequency near the acoustic cutoff frequency. In the chromosphere, oscillation packet of space frequency propagate above. So our view will contribute the determination of atom structure and the understanding of heating and external plasma and the detection of fast waves and alpha that are supposed to be in the solar atmosphere, in the lower atmosphere. So that's all. Thank you.
Thank you very much. Very nice. We've got time for a couple of questions. Yes? Over here? Who's got the microphone? Yeah, this, Shibata-san first.
Yeah, very nice talk. And actually, I have been expecting this kind of research for many years. And I expect this kind of a physical process may be occurring not only in the sunspot umbra, but also other vertical flux tubes. And what is present smallest spot where you can observe this kind of phenomena?
Smallest sunspot?
Smallest case.
Yeah.
According to your observations.
So far, we have been working on sunspot. Actually, I've been working mostly small sunspot. So I plan to extend this kind of study smaller or network features like that. But network feature, it is more complicated because it's not so simple as sunspot.
Not simple.
Yeah,
High
because
spatial resolution.
sunspot umbra seems to be the simplest one.
I can understand. But
So
DKIS may be able to find this kind of.
Of course, but physical modeling is more difficult because you have to think of the environment, place environment like this.
Okay.
Thank you. There was another question.
So you presented your this photospheric resonant layer model and said that from that you get this right kind of period. So presumably it follows from a mathematical analysis. But without getting into the analysis, can one give any kind of qualitative idea how you get that period? Is that given by time scale of something in your problem, or?
That's a good question. Actually, even without modeling, we find that any period of oscillation is very similar to acoustic cutoff period. Why should we have that similar period? That's the question. But the Elmer space is not isomer, so we should pay attention to which point is important. Temperature minimum is the most important. So this kind of frequency is close to the acoustic cutoff frequency of temperature minimum. But why do that? Then we need some theory. That's why I developed this kind of photospheric resonant model.
Thank you. There's a question up the back here.
Yeah. In one of your slides, you showed on harmonics in Doppler velocity. Just can you go to that slide?
Harmonics? Okay.
Yes. So that was harmonics in intensity or Doppler velocity? No.
It's harmonics in the period power of Doppler velocity. So you should have Doppler velocity.
Okay, so can you explain me, because you are observing waves in the umbra, which are vertically aligned lines, and you are finding some higher harmonics. So what does that mean? Like some standing waves kind of patterns, or what kind of?
I can please explain that. You have time sequence of time velocity, the velocity, right? Then if the velocity changes smoothly with time, then you can express a proportion of many frequencies. But since it is very steeply varying, you need a high frequency component. So usually that frequency is twice or 3 times of the fundamental frequency.
Yes.
That's the Fourier principle. So once we have second harmonic, third harmonic, that's the evidence that you have very steep changes of velocity profile.
Thank you.
Okay, yeah, thank you, yeah.
We've got another question here.
Jungchul, the more common understanding of the umbral oscillations particularly in the atmosphere is in terms of the cutoff frequency and the changing of the cutoff frequency because of the inclination of the field, which you have not considered in your scenario. So this, this mode conversion, and in that context, mode conversion is also very well understood now. There is lots of work by Paul Kelly and others, where it is very clearly seen that this is 3-minute is a natural frequency of slow modes in presence of strong magnetic field. I'm surprised actually Marcel is also not commenting on that. So that's very well known now. And the change of the frequency is also because of the inclination of the field is pretty well explained. So now what you're invoking is a mode conversion much deeper in the inside, which we do not have a direct evidence of. So this is, I'm I'm curious to see how this can be further proved.
Okay, this is a sunspot, so inclination is almost vertical. So there is
No, but if you go up, all the inclined fields, it's
okay.
been.
That's why, anyway, the main reason why I'm working on umbral is that you can assume that more or less uniform field and vertical field. Of course, you can think of the inclined field. That's possible. That's another thing. Okay, I'm not objecting to that possibility. Okay.
One last question. One last comment.
So you infer that the source is about 2,000 kilometers below the surface. I'm just wondering, in the model, do you assume that the field is kind of monolithic all the way down to?
Okay, that's a really tough question for me. I have no idea. And that's very difficult to understand because umbral dots are very small. So if we have to combine small size umbral dot and the 2,000 kilometers, then we should think of a column-like convection structure.
Right.
So also we should think about some kind of impulse of compact impact through the magnetic convection, which I have no knowledge. But some theorists may attack the problem. That's my suggestion. Okay.
Okay.
Okay, thank you very much. A lot of good discussion there. Thank you. Next we have Ravitana Ghosh, who's going to tell us about the formation, evolution, and dynamics of trans-equatorial loops. Thank you.
Good afternoon, everybody. My name is Avyarthana Ghosh, and I'll be talking about my work, the evolution and plasma diagnostics in transequatorial loops and their interaction region. I have been doing this work with Professor Durgesh Tripathi here at IUCAA, and this work is currently under review under astronomy and astrophysics. So transequatorial loops, what are those? According to Pevtsov in 2000, nearly 30% of the active regions that are formed on the solar surface, they are actually connected across the solar equator by some long loops which are known as transequatorial loops, and they could be typically 100 to 1,000 megameters long, and they are seen in extreme ultraviolet and X-ray channels only. These are supposed to be global signatures of colloidal fields and have significant contribution in creating large flares and coronal mass ejections. The origin of such loops can be attributed to the Babcock-Clayton model of solar dynamo, which was proposed in 1960s. However, the first observation of transequatorial loops, they came much later in 1970s with XRT Skylab observations. Further down the line with SXT Yokoho observations, Suneta in 1996 suggested evidence of reconnection occurring while these transequatorial loops were interacting with each other. In later decades, elaborate statistical studies have been done by many authors, Pevtsov and Chen et al. Being two of the significant ones. Spectroscopic diagnostics have also been done on transequatorial loops with the advancement of technology, where Hara et al. And Brocius actually did plasma diagnostics in off-limb transequatorial loop structures. But to the best of our knowledge, this is the first detailed evolutionary studies and plasma diagnostics of transequatorial loops and their interaction, X-shaped reconnection region when the field of view was very close to the disk center. So we have used AIA imaging data for evolution studies and extreme ultraviolet imaging spectrometer on board Hinode for spectroscopy. And this will help us to understand the plasma diagnostics at different locations in the transequatorial system. In panel A, we show an AIA 193 angstrom channel image on 12th of December at 1935 UT, where the green box actually is the field of view that is of interest for us and is blown up in panel B. Here we see that there are two active regions on either side of the solar equator, and there are loops belonging to the individual active regions as well as transequatorial loops connecting them. You can see there is a distinct X-shaped morphology of the transequatorial loops at a region where it happens, it looks like there has been a pinching occurring there. The white boxes in both actually shows the field of view of ice raster observations on the same day. So you can see from the image that these transequatorial loops are highly dynamic, and these individual loops and transequatorial loops, they keep coming close together. What happened to the movie? Okay. Yeah, it has stopped working. Yeah. So we can see that these loops are coming and interacting at around this region. There is a pinching off. And we see a lot of dynamic activity going on because of these loops, forming new sets of loops. Yeah. So what we noticed is that the pinching off was occurring at some region which is marked by P here, and we wanted to see the plasma inflow and outflow speeds at this region. So what we do is we take two slits, each 10 arcseconds wide, V and H in mutually orthogonal directions, and we try to find out the time distance variation with time. What we see is that at alternate time at a given time interval, in these two mutually orthogonal directions, the plasma flow is complementary in nature. That is, if there is inflow along one direction, there is corresponding outflow in the other direction. And if you go along one particular direction, either H or V, you can see that at subsequent periods, over 24 hours, there have been alternate periods of inflows and outflows. Typical speeds, however, are very low, about 1 to 3 kilometers per second, but similar low velocity plasma flows have been noted earlier by authors in flaring loops. Here I have also marked four time periods, which is E1, E2, E3, E4, which actually mark the ice raster observation phases. So you see these transequatorial loops have been starting to develop from 10th of December itself, but they become very prominent on 12th of December, and they start interacting multiple times also on 12th of December, where they are very close to the disk center also, and this blue box marks the ice raster field of view. As we progress to 13th and 14th December, these move away from the disk center and also get disoriented. Now, as I was mentioning, on 12th of December, when this loop structure was very close to the disk center, there were 4 ice raster observations which were done. And amongst that, we are going to focus on one which will be identified as E2 henceforth, and that lasted between 1904 to 2005 UT. So taking this time interval of E2, what we notice from AIA 193 angstrom high cadence intensity maps is that there is a particular region which is marked as P2 in these images. Very close to the X region that I have highlighted in first figure, which undergoes repeated brightening, as you can see from the light curve. So by intensity, these are not very bright. These are about 1.6 to 1.8 times the average value. But what we notice is that during one of these phases, when the intensity has actually risen by 1.8 times, ice was actually rastering, ice slits were actually coinciding with that bright region, and that gave us an opportunity to understand the plasma diagnostics of such bright points formed due to magnetic reconnection of transequatorial loops. So from ice intensity maps for low temperature lines like iron 8, iron 10, and iron 12, we see that the transequatorial loops are bright structures along with fairly bright interaction regions. However, at higher temperatures, at temperature increase to iron 12, 13, and 15, we see that the adjacent region, very close to the reconnection region, is actually becoming dimmer and dimmer. That is, plasma is less intense at the exact adjacent location. Oh, come on. Yeah, so we have done plasma diagnostics at the bright point P2, as we have mentioned, and this is to compare this with those in the transequatorial loops. We have selected a region L, which lies exactly on a transequatorial loop, and a region D, which is a part of the loop system belonging to the individual active region on the southern hemisphere. For background or foreground emission correction, we have taken a region at the bottom of the ice raster, which is marked as B here. For density estimates, we have done density estimates corresponding to E2 phase using iron 12 and iron 13 line. And what we see is that the typical electron densities are about log Ne 8.5, 8.61, and 8.8 respectively for P2, L, and D respectively. What we see is that though we don't have any significant change of they are all of the same order of magnitude. Coming to EM loci, so we have done EM loci plots also for these three regions. What is this happening? क्या मतलब है ये? Yeah, it's taking time to go back even. No, wait. Oh, God. I hate this thing. Next one. ये तो आ ही नहीं रहा है. Yeah. Okay, so what we see is that if you remember the three locations that we have been seeing here, I can't show the EM loci maps. Okay. Okay.
Keep it, don't touch it.
Okay, so for the brightening, so for the transequatorial loop location, what we see is that the peak formation temperature lies between somewhere between log T 6.1 to 6.2, with the plasma being mildly multithermal. But at location D, which is a part of the brighter loops at the bottom of the bright region, has more multithermality in nature, and the peak formation temperature is between 6.1 to 6.3. And if you take the bright point P, we see that the peak formation temperature ranges between 6.2 to 6.3, but the significant difference is that we have a small peak at between 6.5 and 6.6. So this suggests that the plasma here has a slight high temperature component as well as compared to the other loop structures. We have also tried to find out the line of sight velocities and FWHM maps for iron 12, 13, and 15. Iron 15 line has been very, Doppler velocity map and FWHM map for iron 15 has been very noisy. So for deriving the Doppler velocities, we have taken wavelength calibration for CCD-A lines using iron 8, and for CCD-B lines, silicon 7. And we estimate that there is an error of about 5 kilometers on the measurements that we have done. We see that the brightening point that we have been talking about, that has significant blue shifts of the order of around 6 kilometers per second. But the adjacent region where we actually observed the dimming of intensity, that has a significant red shift between 5 to 8 kilometers per second, that is downflow. Also the full width half maximum maps that we have shown here, if we convert them, if we try to find out the equivalent velocities, they are about 30 to 40 kilometers per second. So this is a summary of the work that I have done. So you can see that there is significant, red shift at the bright point, and the FWHM, the equivalent non-thermal velocities could be about 30 to 40 kilometers per second. So my conclusions are that we have employed AIA imaging and eye spectroscopic observations for the first time. We have combined them so as to find out detailed evolutionary studies as well as plasma diagnostics in such kind of transequatorial loop structures when they have been very close to the disk center. And we have found out that this is a very classic example of homologous low intensity magnetic reconnections, which have been suggested by Suneta in 1996 as well, based on a SEXT observation. What we understand is that whatever energy is released in this low intensity magnetic reconnection region actually goes into flows and snapping of these giant magnetic loops whenever a reconnection is occurring. So there is no significant increase of temperature of the plasma in these structures, or at the reconnection region, no intensity enhancements, or even release of energy into the heliosphere as flares and coronal mass ejections. Else they remain somewhere trapped within the solar atmosphere itself. Thank you.
Thank you. And thank you for coping so well. Technical difficulties are always a huge problem, particularly when you're up on stage. Any comments or quick comments or questions for Arietana? Yeah, quite a few. Okay. Yep.
Yeah, interesting work. Just a comment that these times as well as these active regions were seen with FOXY. So we have hard X-ray observations corresponding to this. Maybe we can discuss and how we can use this for this. Thank you.
Excellent. Yeah, Dipankar, other people?
So you started by saying that the TACs are important for the CMEs, but in this particular case, you don't seem to see anything. But in general, for the evolution, what's your plan? I mean, what's the big picture? These transequatorial loops, how different they are in contrast to your other loop system. So can you conclude from your analysis?
So since Pevtsov's work actually conclude that nearly 30% of the active regions are having transequatorial loops, they are connected. And if a significant population of these loops actually don't give out flares or coronal mass ejections.
But you can't say significant because you have only studied one
yeah,
case.
So that is a scope that we still have, that we have to do a statistical study of such loops. Now we have so many of observatories and observations that are available in soft X-ray and.
But in terms of diagnostics also, you don't seem to find any difference between the standard loops and the transequatorial loops. No. So that can be concluded.
Yes.
I think it's important to note, it's a very interesting study, but as you say, it's a one-off, but I think it's something you can look for in the future with some of the other instruments.
And maybe this will have, since the energy is not released in that manner in flares and coronal mass ejections, this will have a contribution to coronal heating also. The energy will remain trapped in the corona.
Any other comments or questions? Here? Yep, Mark.
Yeah, so if you don't need to know the the Doppler speeds and the non-thermal line widths, I think you can get similar temperature diagnostics just with AIA alone. So you don't need to confine yourself to the lucky case when ICE was observing this. So that will allow you to do many more cases.
Do you know if anybody has been studying these in general with AIA? No.
Not in terms of the temperature structure.
Okay, something interesting to do. Okay, maybe we'll wind it up there and thank all the speakers this afternoon for some very good talks. And Durgesh has some announcements he'd like to make.
As always, right? Sorry, let me find the program. Not really. We have a public talk this evening at 6:30, from 6:30 to 7:30 at the other institute where many of you are staying. So the buses will leave from here between 5:30 and 6. So please be outside at 5:30. The last bus will leave at 5:45. So if you want to go, you have to get into the bus by then. I also overheard that because the buses will go there, take you for that lecture and bring you back for the dinner over here. I overheard from some people that they may not want to come back for dinner. Okay, so I still invite you to come back because the food is done and it will be just a waste and you will be having dinner somewhere else anyways. So please come back for the dinner because the food is all prepared. I should have asked during lunchtime itself. But in case you don't want to come back, then can I get a number in case if I still can do that? Oh, everybody is coming back. So let's see you in the evening. Come on. So 5:30.
What time are they coming back?
Oh, in half an hour. Half an hour tea break.
Is it off? Is it on? Okay. Off. Please. Hello? Can you hear? No? Hello? No? Okay. Your kind attention, please. Welcome to this last session of today's meeting. And I have been asked to conduct this session strictly within 1 hour so that we are ready to catch the bus to go for evening talk. So there are 3 talks. The first talk is by Professor Michael Wheatland. I invite him to start his talk on coronal magnetic field modeling.
All right, thank you, Bowler. Yes, so. All right, I'll pay attention. Okay, so I'm Mike Wheatland from the Uni of Sydney. I'm talking about challenges in coronal magnetic field modelling. This is work done together with Vic Demsak, Alpha Mastrano, and Kai Yang at the University of Sydney. So just to provide some motivation for the problems, why do we want to model coronal magnetic fields? Magnetic fields in and around sunspots on the sun in active regions provide energy for solar flares and coronal mass ejections. And these examples of large-scale solar activity produce space weather events, produce bad space weather in our local environment. So what we'd like to do is to be able to model the magnetic source regions for this space weather, to try to understand it, to try to predict it. The diagram here shows active region 12673 from September 2017. So that was a big active region in the declining phase of the last solar cycle that produced the biggest flare of the last solar cycle. It produced a series of large flares. So we'd like to understand that behavior in active regions by modeling the magnetic field that is there. So there are a variety of approaches that people use. The magnetohydrodynamic approach is a full dynamic approach. It involves the dependent variables, the velocity, the magnetic field, the pressure and the density. So it's an initial value, boundary value problem. You have to specify initial values for all of those dependent variables and then boundary conditions on them as you evolve the system in time. So it's quite involved, computationally intensive. But data-driven MHD is really a growing area. It's great progress has been made there. I'm not going to talk about it anymore. There are, however, some talks later this week by Yang Guo and Satoshi Inui describing examples of data-driven MHD. A slightly simpler model is a magnetohydrostatic model where the dependent variables then are the magnetic field, pressure and density. There are various solution methods for the magnetohydrostatic problem. There are examples of approaches that are like numerical extrapolation, and so I've given a couple of examples there. A common approach is the nonlinear force-free modeling approach. In that case, you're just solving a boundary value for the magnetic field. So it's particularly simple in that way. It's less computationally intensive than than MHD, for example, and simpler in some ways. And it's now routinely used, I would say, for extrapolation of magnetic fields from solar boundary data at the photosphere. There are also hybrid approaches that involve elements of these different approaches. So, for example, you can do MHD modeling with the nonlinear force-free field as an initial condition. In that case, the advantage is that you start with a field that's already got free energy. And there's also the flux rope insertion method that Adven Ballyhooen pioneered. I mentioned the nonlinear force-free. That nonlinear force-free modeling's become very popular. Here's a slide illustrating that. It just shows some examples of images from papers in the last couple of years where people are using the nonlinear force-free modelling approach, doing extrapolation to identify structures that are there in the magnetic field, to quantify electric currents that are there, and to determine the topology of the field structure in particular active regions.
So the challenges that are there in the title. I would say that despite the wide use of the nonlinear force-free modelling approach and the other approaches as well, there are still basic problems. In particular, the boundary data, the solar boundary data, may be inconsistent with the modelling with the model that you're using, and that can lead to problems. Also, there's no ground truth on the magnetic field there in the corona to validate the models. That's a basic problem. And related to that, I think the models are often interpreted rather uncritically. So what I'll do here is I'm not going to talk more in detail about these generalities of the problem. I'm just going to talk about some specific things. I'm going to show a simple test for the divergence-free condition for a magnetic field. I'm going to show an investigation of nonlinear force-free reconstruction for highly twisted magnetic fields. And also I'll present briefly an alternative definition for relative magnetic helicity that gives some insight into relative magnetic helicity, I think. So first, the divergence problem. So the methods we use to calculate these coronal magnetic field models may produce a solution that has a non-zero divergence for the vector field. So it's not, in that case, it's not a physical magnetic field that you've calculated. And this may be due, for example, due to the inconsistency that I mentioned between the boundary data that you're using and your model. That can lead to this problem. And the error that's there then can affect various quantities you calculate for your field. For example, the energy of the field can be inaccurate. There can be contribution from a non-solenoidal component of the field. And Gerardo-Vallori has presented a way to quantify that. It's a Helmholtz decomposition of a vector magnetic field in a volume to identify the non-solenoidal component and to work out the energy contribution due to the non-solenoidal component. Here I'll just discuss something that's much simpler, that relates to the question of calculating the free energy of a magnetic field. So if you want to calculate the free energy of a field, what you normally do is decompose the field into a potential component, BP, and a non-potential component, Bj, where your potential component B is if it's the usual reference potential field, it matches the normal component of the total field on all of the boundaries of your volume. And then you calculate the energy of the non-potential component, which is the total, which corresponds to the total field minus the potential field. That's only one way to do that calculation. You could also calculate the free energy as the total energy minus the energy of the potential field. The relationship between those two estimates is given in the box here. So the difference is a volume integral that involves the divergence of your field B, and also phi there is the potential corresponding to your reference potential field that has a normal component matching the normal component of the total field on all boundaries. So the two estimates then are equal if the divergence of your field is zero everywhere in the volume. So it gives you a necessary but not sufficient condition for a divergence-free field in the volume. It provides a test in that way for meeting the divergence-free condition for your calculation. So I'll just mention again that you have to use the potential field here that's calculated with a potential that's obtained by solving the Laplace equation for the Neumann problem on all of the boundaries of your volume. So that is important. So to illustrate this, I'll just show this one calculation that Alfa Mestrano did. So this is looking at the fractional difference between the two estimates. That's this parameter epsilon up here. And it's calculating that fractional difference for a set of nonlinear force-free calculations. So so there was an EC workshop that Mark DeRosa and I ran where a range of different nonlinear force-free codes were applied to boundary data for active region 10978 from Hinode. It was Hinode data. And for that data, the data was used to construct effectively magnetograms with different spatial resolution by rebinning the Hinode data. So what this plot shows is that fractional difference between the two estimates versus the bin number for the data, and then the different lines correspond to the different solution methods. So what you can see here is that this square is for the optimization method for calculating nonlinear force-free fields, Thomas Wiegelmann's method, and in that case the calculations that were made don't pass this test. So there's quite a significant difference between those two estimates for the free energy. For the other solution methods, which are the magnetofrictional method and three Grad-Rubin type codes, my code, CFIT, and two codes that Taha Amari wrote, overall the the difference between the two estimates is relatively small, although there's some interesting deviations here that you can see in those results. So what I'll stress here is that these results illustrate the need to check the calculations that you make, just to check that you are solving the problem you think you're solving, obtaining a force-free magnetic field. And the two free energy expressions provide one simple way to do this. All right, so for the second topic here, I'm just going to talk about reconstruction of highly twisted magnetic fields, an investigation that Vic Demsak has performed. Vic's a PhD student working with me. So coronal field reconstructions are often used to investigate the topology of magnetic fields in the corona, but the checks on the results are often rather indirect. So one topological feature that's of interest is the bald patch, where magnetic field lines are tangent to the photosphere. It's interesting that you can identify a bald patch from the vector magnetogram data alone. It's just defined by this condition on the field components at the neutral line. However, if you do a nonlinear force-free reconstruction, you may not reproduce a bald patch, even if there's one there that you know from the data, because the reconstructions change that horizontal field in general. So the Titov-Demoulin field provides a test case for reconstruction that contains a bald patch. Here's a little diagram showing the Titov-Demoulin flux rope and this bald patch where magnetic field lines associated with the flux rope are tangent to the photosphere. So what Vic did was to do a series of reconstructions of the Titov-Demoulin field using the Grad-Rubin nonlinear force-free code CFIT, and so he applied that code to boundary values taken from a direct calculation of the Titov-Demoulin field. The boundary conditions on the model that are extracted are the vertical component of the magnetic field over the lower boundary of a Cartesian volume, together with values of the force-free parameter alpha, calculated in this way at the lower boundary, is the ratio of the vertical component of the current density and the vertical component of the magnetic field. Now I'm spelling that out because with the Titov-Demoulin field, it's not an exact force-free field, so there's no unique definition of that alpha. So that's the definition of the alpha that we're choosing here. So the boundary conditions then are the normal component of Bz over the lower boundary, and we use then the values of alpha over the positive polarity, or the values of alpha over the negative polarity, or the third choice was to use the values of alpha over both polarities and to use the self-consistency procedure. So the results are different because the Titov-Demoulin field again is not quite force-free. It's an approximation to a force-free field. The fields that we used had the same geometry for the flux rope, the same size and shape of the flux rope, and the same burial depth, and also the same values of the buried charges that are there in the model. What we did was to vary this line current that is there beneath the photosphere in the model. What that does is vary the wrapping azimuthal field that's in the corona, and if you keep the other parameters in your model fixed, then that changes the twist number for your flux rope. So if you increase that line current, then you decrease the twist number because you're increasing the if you increase the I naught, you decrease the twist number because you. Have I got that right? Increase I naught, you decrease the twist number. Certainly right. Yeah, you're making the azimuthal component of the field here in the flux rope more important in that calculation. So that's right, yes. Okay, so that's what we did. Here are the actual parameters that we used in the calculation. So these are the different parameters for the Titov-Demoulin model. These are the values. So here we're decreasing that wrapping, the line current. We're increasing the twist number, as I mentioned. So these fields are. So there are 5 cases that were considered. 4 of them there have a bald patch in them. It's interesting also that a number of these cases are likely to be kink unstable in a dynamical equilibrium of the field. The kink instability depends on the average twist angle in the coronal portion of the flux rope, also the aspect ratio of the flux rope, and the boundary conditions on the evolution. So it's not entirely certain, but they're highly twisted fields. That's true. Okay, so I'll show you the results then. What I'll show first is the first case is case 2, where it's a moderate twist number. It's not a particularly twisted case. So this top left panel here shows the Titov-Demoulin model directly calculated. We're looking down on the volume. The colors represent the vertical component of the current density in the boundary. The field lines, the green field lines are field lines from near the center of 1 foot point of the flux rope. The black field lines originate in the bald patch that's there in this model. So on the right-hand side, in this right-hand column, you've got the P and the N solutions, and this is the self-consistent solution. So for example, with the P solution, the boundary conditions on the electric current density on the positive polarity are preserved. Where the field lines map to depends on the model, so that's different in this model. You can see that the green, the field lines at the center of the flux rope are approximately reproduced, and you get ball patch field lines here. The N solution is similar, just interchanging the two polarities. The self-consistent solution isn't as good and isn't as good in the sense that it doesn't reproduce a bald patch here. So that's a consequence of the averaging that occurs in that self-consistency procedure. Here's a more highly twisted case. So here the twist number is almost 9. You can see this very twisted set of field lines associated with the bald patch. These are the reconstructions, the P and N reconstructions. So you can see that they recover a bald patch, but the field is rather distorted. So there's some difference in the results that you obtain from the original field, and that's due to the fact that again, the Titov-Demoulin field is not exactly force-free, and this is the self-consistent solution, which tends to smear out those electric current, the current density values, and again, you lose the bald patch. Okay, so another way of looking at this is just to look at the vertical values of the field in the boundary, BZ in the boundary, the neutral line, and the neutral line is, so the colors are the vertical component of the field, the yellow is the neutral line, the black patches identify where the bald patch is. So you can see that the bald, here in fact this field had a bifurcated bald patch. That's not recovered, you just get single bald patches in the P and N solution, and the self-consistent solution doesn't recover the bald patch. And finally here's the highly twisted case, which is similar but different in details. To conclude on this point, this shows that it's possible to reconstruct these highly twisted magnetic fields, including a bald patch. But there are various departures from the original model due to the fact that it's not exactly force-free. It's also interesting that that self-consistency procedure in this case doesn't give us any advantage in the reconstructions. Okay, so my third topic is magnetic helicity. I'll talk about this briefly. So the definition of magnetic helicity is that it's the volume integral of the magnetic field dotted with the vector potential for that field over a volume. And you can interpret that as follows. If you consider the line integral of the vector potential around a closed loop, then it's easy to show using Stokes' law that that's minus the flux, magnetic flux that's passing through your closed contour. And then using that, it's easy to show from this that for two simple isolated untwisted flux tubes drawn here, just two little contours which are flux ropes if you like, where the field everywhere else is 0, then the magnetic helicity is plus or minus twice the product of the fluxes. So this tells us that the magnetic helicity is some measure of the linkage of field lines. More generally with flux ropes, they will themselves have twist, which will also contribute to this helicity. So it's a measure of the linkage, the twist of field lines. However, with that definition, if you consider a change of gauge for your vector potential as shown here, then that's the change in the magnetic helicity. And so you can see it's only gauge invariant if the normal component of B is 0 on the boundary of your volume. So this definition is only gauge invariant for a closed magnetic field, you can say. So this problem was solved, apparently, by the introduction of the relative magnetic helicity, which is defined as follows, as shown there, where BP then is a reference field, and AP is the vector potential corresponding to the reference field, where that reference field has a normal component everywhere on the boundary that matches your field B. So this is the definition of relative magnetic helicity, and then the change under a change of gauge, this is how the magnetic helicity transforms, and you can see that because your reference field matches the field B on the boundary, then it's gauge invariant. So that's the point of introducing that. So this definition of relative magnetic helicity has been widely used. The reference potential field BP is generally taken to be the potential field that matches that has a normal component matching the field B on all boundaries. And in that case, we have the field. We've effectively introduced a field decomposition that your total field B is this reference potential field, with a normal component matching B on all boundaries, normal component of B on all boundaries, plus a non-potential component to the field Bj, and so that non-potential component must have 0 normal component on the boundaries. It's a closed non-potential field. So this reference potential field by the Thomson theorem is the lowest energy field matching those boundary conditions. So with that decomposition, then you can rewrite the magnetic helicity as the sum of a self-helicity and a mutual helicity, where the self-helicity is the linkage of the closed non-potential magnetic field with itself, and the relative helicity is the linkage of that closed magnetic field with the open reference potential field that you introduced. And both those things are well defined. That's essentially why this definition is well defined. Okay, so now I'm going to talk about a different definition of relative magnetic helicity based on a periodic potential field. So this is a more restricted definition in a number of ways. One is that I'm just going to restrict the discussion to a Cartesian volume, and I'm going to define an up and down. So if you can consider that situation, and you could decompose a field in your volume into a current carrying field and a periodic potential field. So here I'm going to use a periodic potential field B0, where B0 has a normal component matching the total field on the top and the bottom boundaries, but has periodic boundary conditions on the transverse, the side boundaries. So in this case, the non-potential component of the field is not a closed non-potential field. And correspondingly, this B0 correspondingly doesn't have a normal component matching B on all boundaries, the normal component of B on boundaries. So you can't use that B0 in a definition of relative magnetic helicity. The result won't be gauge invariant. But here's a point. It's of interest to use that periodic potential field because it turns out that if your total field B is periodic, the energy of that periodic potential field is actually lower than the energy of the usual reference potential field that matches the normal component of the total field on all boundaries. That's not obvious, but you can get some insight by identifying that the boundary conditions on that field are less strict. You're only matching the normal component of the total field on the top and bottom boundaries, and in the side boundaries, it's periodic. So there's more freedom in that field. Okay, so you can take that, so we've introduced now this alternative decomposition of the field using the periodic potential field. You can take this non-closed, this open current carrying or non-potential field, you can decompose it into a closed current carrying or non-potential field and a potential field where the potential field is constructed to have a normal component matching the normal component of BC on all boundaries. Okay, and given that, we can then define a relative magnetic helicity for this field for the open non-potential field BC. Here's that definition, like that. Okay, so we've now got a decomposition of this open non-potential magnetic field BC, defined by our periodic potential field and our total field. And so then, correspondingly, we can decompose our new relative magnetic helicity into a self-helicity and a mutual helicity. The self-helicity is now the internal linking, the self-linking of this closed non-potential magnetic field that we've constructed, and the mutual helicity is the linkage of that and the open potential field BP1 that we've introduced that has a normal component matching BC on all boundaries. So it's analogous really to the usual definition of relative magnetic helicity, but a bit different. Okay, you can consider both decompositions applied to a field. The usual decomposition with the standard reference potential field with the normal component matching the total field on all boundaries, and our new decomposition with the periodic potential field. So it's easy to identify then that the two closed non-potential magnetic fields, Bj and Bc1, must be the same. They have the same boundary conditions, satisfy the Poisson equation, they must be the same. And this is the relationship between the potential fields. Also from this, we can then go back, and because of this relationship, the fact that these two closed non-potential fields are the same, we can identify that the self-helicity this self-helicity is the same as the usual self-helicity in the definition of relative magnetic helicity. And moreover, if our field BP1 is small, then our new relative magnetic helicity is approximately equal to the self-helicity in the usual definition. That's complicated, but I got it right. Okay, so to illustrate this definition, you can take, again, the Titov-Demoulin equilibrium, and what we did was we did a sequence of reconstructions where we had the flux rope with, and changed the burial depth, reduced the burial depth, and in that way it's a poor man's version of a flux rope emergence, if you like, into the computational volume. And so here are the results that we obtained. This is for the energy as the burial depth decreases. This is the magnetic helicity. And so to cut this short, I'll just point out a couple of things. Here's the solid line here is the total energy. As the burial depth decreases, you've got more of the flux rope in the volume, the energy goes up, and it goes up more and more rapidly as this depth goes to zero, because you've got the singularities along the axis that are approaching the bottom of the volume. Here are the different definitions of the magnetic helicity. The dotted red line is the usual relative magnetic helicity. The dotted blue line is our new definition, and the solid line here is the self-helicity for the usual relative magnetic helicity. So you can see in this case, indeed, they are approximately equal. Okay, so I'll put up the summary there, but I think I've already described all of these things, and I'm running short of time, so I will stop there. Okay.
Questions, comments, suggestions? Yeah.
Okay, sure. Thank you for the very interesting talk.
There you are.
So my question is that if you could please go to the slide where you decompose helicity into the yes. You have decomposed it further where you have a potential component and the current carrying component. So, I mean, what advantage could it be like for this approach, calculating helicity from this approach, from the conventional relative helicity? So, because you have, in BC, you have BCL plus BP1, so there is a further potential field component. So, as you mentioned in previous slide, that the, B0 has lower energy. So, but BP1 will also add that energy to the potential field. So, wouldn't it be the same energy then overall?
I didn't catch the last one.
I mean, like the B0 has lower energy than the BP that is considered in other cases.
Yes.
So, but there is another BP1 that is also there.
Yes.
So, so what would be the advantage of using this approach?
Well, I think there's two things I would answer. One is that B0 is a lower energy field, so it's of interest to use that in your decomposition of the field to begin with, and to calculate a free energy using the minimum energy against the minimum energy field. That's important. That's the first point. The second point is that this is kind of a construction. It illustrates the freedom that's there in the definition of relative magnetic helicity, which I think people don't appreciate. You know, the reference field only has to be a field matching the normal component of the total field on the all boundaries. Moreover, there's it's a construction using this reference potential field. We've done a different construction using calculating a relative magnetic helicity for a different field, which is also a valid relative magnetic helicity. It just describes something slightly different.
So, are you going to try it for some active regions and find out the values of helicities from this approach?
Yes, Kai Yang did these calculations. So far I showed briefly the Titov-Demoulin calculation with the flux rope. He also did an MHD eruption of that flux rope, and yes, we will try it for other data, including solar data. Yeah.
Thank you.
Sure.
This may not be related to reconstruction, but the original getting the magnetic field from data. So there is this famous 180-degree problem, 180-degree ambiguity.
The ambiguity in the field transverse.
Are there any new developments in that?
I don't think that people have worried about that so much. I think that the error is there sometimes. I mean, there have been tests done with synthetic data, where you see how well the standard methods do, and they do reasonably well. So I think
have they gone to very high resolution magnetograms to test that, model magnetograms?
Yeah, I'm not sure about that. Yeah. Yes, it's a good point. Yeah, there's lots of uncertainty in the modeling we're doing. That's another aspect.
Yeah, if I understood you correctly, you said that some of your codes for reconstructing this magnetohydrostatic solution make divergence B is equal to non-zero. So I was wondering how large this non-zero is. For example, you can get a length scale by dividing B by divergence B, if divergence B is non-zero.
Yes.
So how large are these length scales? Are they much, much larger than the system which you are modeling?
I think the problems are localized when they do these calculations, that you know, if you use that optimization method, the problem is that you've got a forced lower boundary, and then you evolve this thing to be approximately force-free. But if that lower boundary, it's not forced, if it's inconsistent with the force-free field. If you evolve it and you've got that inconsistency, you have to have departures somewhere. And I think they're localized. I mean, you see that, yeah. It's a good point. I haven't thought of calculating a length scale. Yeah.
Okay. If there are no questions, I think let's thank Michael once again. May I invite Julio to give a talk on evaluation of coronal magnetic field in the current cycle. Huh? No, it's not. See, this ends with Raman. That's it. It ends with Raman stock. That's it. That's the last one. Okay. This is lectures only. Yeah, that's fine.
Okay.
12 minutes, stand, just give you a hint, and then
Okay.
you try to continue. Yeah.
Okay, I'll try to see you.
conclude in 12 minutes.
Okay.
Thank you.
Thank you also. Hello. So I will talk about coronal magnetic field evolution over the solar cycle 24. Yeah, we know that the effect of the solar cycle has a print in the sunspot numbers, but also in the intensity of the magnetic field over the full disk during the minimum and maximum of activity. And we can see this effect also in the corona from minimum to maximum of activity. While there were many studies which were dealing with the variation of the sunspot numbers and of the magnetic field in the photosphere, at the coronal level, there were not so many studies regarding this aspect. And this may be because it's difficult to obtain magnetic field measurements in the corona. We already heard about that. And this due to the fact that the magnetic field strength is low at such altitudes. And coronally, it's optically thin. So because of these aspects, people are trying to do to derive the coronal magnetic field through magnetic field extrapolations. And as we heard already, one of these extrapolation, it is nonlinear force-free field extrapolation, which are using full vector magnetic field as a bottom boundary. And it has as assumptions low plasma beta in the corona, so the magnetic forces dominate over the plasma forces. It also assumes magnetic field in the corona being stationary, so no flares or coronal mass ejection. And then the force freeness, it is fulfilled if the Lorentz force and the divergence of the magnetic field are vanishing. And force-free the extrapolation which we are using, it's nonlinear force-free field optimization method, which was initially proposed by Whitlands, Turok, and Romeliotis, and then implemented by Wigelmann. And what it does, it minimizes this function, and the first two terms are exactly this one, so it minimizes the Lorentz force and the divergence. And the third term, it's trying to bring the model field closer to the observed one at the surface level, at the photospheric level. We applied this method for HMI data more exactly for synoptic magnetograms obtained from HMI onboard stereo in this time frame. And these synoptic magnetograms are constructed during a Carrington rotation cycle, and they are constructed from HMI full disk vector magnetogram. So each column of the map, it's a particular Carrington longitude at its central meridian passage. After we apply the data, the extrapolation, we calculate the unsigned flux from the photosphere into the corona, and we made a distinction latitudinal dependent. So we choose the southern region, and for the photospheric level we plotted here with blue. We made the northern hemisphere between 30 degree and 70, and here for the photospheric level it's with red. And then we made a distinction at the center between -30 and 30 degree latitude. And within this region, we separate between flux, which is coming from the sunspots. And this we select this flux larger than this particular value. So only the magnetic field, which was coming from regions larger than this value, we were taking into account to calculate the flux from the for the sunspot. And here with the red contours are these, the contours represent this maximum value which we consider for the calculation. And this flux from the sunspot, it is plotted in here with violet. And then also in the center region, we consider the faculae flux, and it was everything else which was not sunspot. And we plot it here with green. And here we show also the variation of the sunspot numbers. And we show here the 2 peaks of the sunspot, and here another region which we consider. So in the center region, our flux is the most similar with the variation of the sunspot, except this R3 region, in which we can see an enhancement in flux in this plot. Then another observation, it is that the flux coming from the faculae, it's the main contributor to the total flux, which is plotted in here with black. And the sunspot, the flux coming from the sunspot, it's 1 order of magnitude lower. And another observation would be that we can see an oscillatory pattern at different, let's say, frequency and amplitudes already in the sunspot numbers and in the flux, and maybe a little bit less. And the most we see it in the variation of the northern and southern region flux. Now we also calculated for the corona, and here in the left panel you see the temporal variation of the flux coming from the faculaes, the sunspot, the north-south region at 3 different altitudes above the surface, so 1.4, 1.8, and 2.2 solar radii. And we can see, and here in the right side, you can see the total flux at also different heights in the corona. And in all of them, we can see that this R3 region, which is right after the second peak, it has the, it looks very prominent. And as we go higher up with height, it has an enhancement relative to its curve. Okay, and here I plot the variation with height of the average percentage contribution from each of these components with height. So we can see that the faculae flux had the main contribution at all heights for all of the cycles, followed by the southern region contribution. Okay, we calculate also the north-south asymmetry between the two hemispheres now. And we looked at the normalized asymmetry index for 3 different heights. And an asymmetry index higher than 0, which shows that the northern hemisphere is dominating. And equal to 0, it means that the two are symmetric. And here, again, the sunspot number variation, just for placing to know where we are. And we can see that in the photosphere, the green dots in here are showing that in the descending phase, after the R3 peak, so which is around here, the northern and southern hemisphere are closer to the symmetry. And at altitudes of 1.8 solar radii, the more brownish symbols in here are showing that in the ascending phase in here and in the descending phase after R3, the two hemispheres are symmetric. There are studies, and one of them is Temor et al. In 2006, which are saying that the sunspot asymmetry, it is present at the beginning, at the end of the cycle, and she was concluding that from analyzing cycles from 18, the cycles 18, from 18 to 23. But she was also referring to other studies which were saying that that one can see symmetries at the maximum of activity. Okay, we calculate also the magnetic free energy, which is the excess of energy of over the potential energy. Yeah, the potential energy being the lowest possible energy. And yeah, we say that the magnetic energy, the free energy, is a proxy for the probability and the strength of the dynamic processes in the corona. And we can see, and we plot it here with time, okay? And in the first part of the cycle, the free energy enhancement, we can see it at the first minor peak. It is larger than how it is at the peak 1 of the sunspot. And in the second part, the free energy is similar to the unsigned flux dominated by this R3 region. So here we find the highest enhancement in the free energy, practically. And then we compare our result from the free energy with the flare index, which is roughly proportional to the mean energy emitted by flares and its duration in minutes. And we made this plot using the source data from Candili Observatory. And we find a correlation between practically the model and the observation somehow, a correlation coefficient of 0.88. And here in the flare index, we can also see that the maximum index it is in this R3 region, as we call it. I also derived the magnetic field at 1 AU based on the modeling. So we first mapped the open field at 3 different heights, and then we derived this magnetic field at 1 AU. And we compare it with the observations. And here we plot practically the ratio between the observed field at 1 AU taken from OmniWeb data centers, so from in situ measurements, and over the calculated field at 1 AU. And these high values, it means that we practically underestimate the field at 1 AU. But here in this region, close to this R3 region, we have a quite nice ratio of almost 1. And here at the end of the cycles, again, it's a quite good estimate, let's say. Okay, and to summarize, we calculate temporal variation of the total unsigned flux in the photosphere, and it resembles to the sunspot number except of the R3 region, which is right immediately after the second peak. and this R3 region is the highest peak in the flux evolution. And this unsigned flux from the faculae is the main contributor to the total flux and not the one from the sunspots. And using the nonlinear force-free field method, we model the magnetic field in the corona during this cycle 24. And the unsigned flux show an increased enhancement again at this R3 region with height relative to the rest of the curve. We derived the temporal variation of the free energy from the solution of the extrapolation, and we find a good correlation with the flare index. And we were tracing this magnetic field to the 1 AU, where we could see also in the observation data this enhancement at the R3 region. Thank you.
So it was a wonderful talk on evolution of magnetic field in cycle 24. So I have time for one quick question. Quick question, yeah, okay.
So you showed that the contribution of the faculae is the dominant. So did you also compare, because in your own institution there is also similar work with the plages and the irradiance variations. So did you try to compare, their results with your type of modeling?
No, not really. But how did they make this separation?
No, they have a very sophisticated model. You should talk to Sami and the rest.
I have seen other studies, yes,
yeah.
And they were doing this separation between, let's say, they were doing a separation. They were taking the entire active region and.
No, they have a contribution from the plages, so the plage index.
Different region of the flux. And yeah, but just taking the plages, no, I haven't seen it, but I will be very happy to know about it.
Okay.
Any other comment? Yes.
Yeah, I have a quick question. For you showed you have this nonlinear force-free open magnetic flux. So, what kind of region is it?
What kind of region?
Yeah.
What do you mean?
What
so
kind
we
of
can
region
map the open magnetic flux at different heights. So that means we trace the magnetic field lines, and we see at the height of 2 solar radii, where is it the magnetic field still open?
Yeah, I mean, like, what kind of magnetic feature correspond to this kind of?
I didn't yet make this comparison. I mean, I have these maps of open magnetic field, and yes, it can be compared with EUV synoptic maps, and yeah, in principle, it should fit very well with the coronal holes.
Okay, thank you.
Okay, so thank you very much for wonderful talk. Now I invite Dr. Ramit Bhattacharya. So on the topic on the 3-dimensional nulls. So I give you, how much time need to present? 10 minutes plus, I'll stand up and then we will have.
Okay. Good afternoon. Let me first clarify that I do understand the responsibility of the last speaker of the last session. So, I will try to be as quick as possible. Now, as the title reads on three-dimensional magnetic nulls, but the talk will be very much focused. What I am going to impress upon you is a cartoon like this. So, you start with a magnetic field line, any arbitrary magnetic field line, let it relax through magnetic reconnection, and at the end you generate a nice three-dimensional null, okay, which can be seen here. Before we get into that, nulls are basically, as you know, that they are first and foremost, they are points where magnetic field is 0, right? And if the magnetic field is 0, then that can be kind of envisioned using the magnetic field line, where the point where the field is 0, the magnetic field lines will try to kind of avoid it. So, if I shoot a bunch of field lines from above and a null is here, they will come and get fanned out like that, and if I shoot the field lines from here, then they will come up and they will fan out again. So, these planes where they fan out are called the fan plane, and the two axes along which the field lines are shot are called the spine axis. And in sun or the solar photosphere or near the chromosphere, actually we do find this kind of magnetic nulls. This is one such topology. It is actually extrapolated from vector magnetogram, neither using the nonlinear force free nor the linear force free nor the potential. It is a new model, but I will get into it. So, as you can see that since the field lines are to be anchored, so it is kind of the field lines which started from the top. So, these are the field lines. They came down, funneled out, got anchored, and so this is like an inverted funnel. And whereas the field lines which started from the bottom, so these are the field lines, actually they go up and come back like a fountain. And by the way, this is a flux rope, the red colored field lines contained within that structure. Now, they can be potential like this one, or they can be current carrying like this one. You can see they carry current because your field lines are kind of deformed. Now, magnetic nulls may or may not come isolated. We feel that they should not come isolated. This is one more picture of three-dimensional null. So, these are the three-dimensional nulls. I can see them from here very well. So, this is one such null, this is another. And please see one thing, that if the field line, okay, is actually going out from this particular null, then for this null, those field lines are actually coming in. And whether a field line will go out of the null or whether they will come back to the null actually determines the topological degree of that particular null. Okay, so when the field lines come toward the null, they have +1 topological degree, and when they go away from the particular null, it is -1 topological degree. And I do not want to get into the mathematics. The mathematics is well defined and well understood. What it tells is that, and this is a very stringent condition, that the overall topological degree has to be conserved. So, if I start a system where there is absolutely no null and I want to create magnetic nulls in that system, then I should create them in pairs. Okay. So, the next thing is whether do we expect these nulls really in nature or not. But before that, even I want to tell you where the nulls can be seen. I mean, they are almost ubiquitous. You can see them in magnetotail So you have coronal jets which are actually initiated by the nulls, reconnection at the nulls. So I would like, or rather request you to see these posters where really stuffs are done which are more more direct to solar physics, where extrapolations are done and magnetic nulls are shown to be responsible to onset magnetic reconnection. But one question still stands, and this question was asked to me by none other than Gene Parker. So the question he put forward was very simple. He said that, look, how do you create the nulls? Say you have n-1 magnetic dipoles here, okay, and at a point P, the magnetic field due to this n-1 dipoles is plus B. So what you do to create the null is you take one more nth dipole, bring it in such way that at P the magnetic field due to the nth dipole is minus B. So B minus B is 0 and this point P is a null. So already you can see this is a special or a tailored configuration, that is I am configuring, I am actually using a particular geometry to get a specific outcome. Now in sun where you have so much reconnection is going on, if it is a active region, if it is a flaring region, then what really guarantees, or do we really expect that such special configurations will be created, and if created, will they exist for long enough to reconnection to occur? Okay. So the question is whether they are oddities or are they expected. So to me it came something like that whether can these nulls be spontaneously generated or not. So we kind of worked on it. I will show you only result of one simulation. So we performed basically magnetohydrodynamic simulations to see, and for that we have started with a set of magnetic field lines. This is a single field line, trust me. So as you can, some of us can recognize that this particular field in fluid dynamics is known as the Arnold-Beltrami-Childress law, which we have used as magnetic fields because Arnold-Beltrami-Childress law is also incompressible. So if I plot the field line, and this is one single field line, the field line actually ergotically fills up the whole volume and is chaotic. And we choose the limit C which does not belong to this constant C which does not belong to this region, such that, I mean, if I fix C in this region, there won't be any null in the system. And then we did the simulation driven by mostly by reconnection, and you can see the nulls appearing here, here. And the way we detected the nulls is by using this formula. You can see that I can set B0 to be a very small number, near 0 maybe 10 to the power minus 4 minus 5, and only when B is near the 10 to the power minus 5, psi has a value. So I am detecting isosurfaces of those points. Okay. And then we actually kind of stopped the code when we had the nulls generated, and I would like to draw your attention to this set of figure. Already you can see that when you look at a figure like this field lines, and if you recall the field lines which I have shown earlier, they were totally disordered, chaotic, and these are quite ordered. So I am generating already order from chaos. This is self-organization, right? And not only that, if I plot the field lines near the null, then you can see for every field line, okay, which is where a field line is going away from the null, I have field lines which are actually going toward the null, so that the topological degree is once again maintained. Here it was partially maintained, I must say, but that we believe is because of our what you can say, shortcoming in detection of all the possible nulls. But nevertheless, kind of with certain amount of confidence, we can say that although these are counterintuitive, but the 3D nulls can exist because of self-organization. And one more thing I would like to say at the end as a teaser, that you see, self-organization is connected with the long-range ordering. Long-range ordering means decreasing Shannon's entropy. Okay. So if I really decrease entropy, then I am going against thermodynamics. That is why I need magnetic reconnection in the system to offset that reduction in decrease of entropy, so that as I reconnect and generate heat, a part of the entropy will keep on increasing, so that the total entropy of the system always increases. So thank you very much for listening.
So although we don't have time for questions, but Ramit might not forgive me. I have time for one brief question, please. Any comment? Yes,
yeah.
Michael.
Can I just ask about that magnetic field model at the beginning? Because it looked like it had a real kink in the field line.
This one?
No, right at the beginning, before the nulls.
This one?
It had a null as well. No, right at the beginning. Yeah, that one. You've got kinks
this one
in those.
or this one?
On the right-hand side.
Yeah. This you can see this.
Yeah, but there.
This guy is actually kinked.
Yeah, but
the flux slope.
Right there. Just you can see it's
here.
like there would be a slingshot effect. I mean, there'd be a very strong force there.
Here.
Yeah.
Yeah. That is because it is neither potential field nor it is linear force free. So there is something called a non-force free extrapolation technique.
Okay.
Where you superpose two linear force free fields.
Okay.
Which do support a current.
Yeah.
So that is why you have
it's not force free.
That is why you have the deformation in field line.
Yeah. Okay.
Thank you.
Thank you.
So in the end, this was the last scientific session, and let us thank all the three distinguished speakers of this session. So buses are waiting. So that's the reason that we have just finished on time.